Good afternoon and welcome to ARA's Webinar Wednesday program. I'm Jerry DiMaggio from the Southern Delaware Office of Applied Research Associates. I'll be serving as moderator for today's program entitled Airport Pavement Management, Past, Present, and Future. I'll first be making some introductory comments and rejoining the program at its conclusion for the Q&A program. Next slide, please. So just a few housekeeping items. If you're having an issue with your sound and you're using computer speakers, please dial in using your phone. And if you're having another issue, you see highlighted on slide number 2, the slide numbers, by the way, are located in the lower right-hand corner of each PowerPoint slide. If you're having another issue, please use the chat button, send a message. Only send that message to the host, please. Next slide. We encourage you throughout the program to ask questions. We'll accommodate questions as best we can. And each of our speakers, those of you who've joined us before, make themselves available generally for at least 2 days following the immediate program to address questions that you may think of at the conclusion of the program or during the program if we run out of time. Now, when you click on that Q&A button, make sure you direct the question to both the host and the panelists so we can see the questions as they come in. Again, we encourage you to do that during the program. Also, as a reminder, and I'll be mentioning this at the conclusion of the technical program, the full presentation that you'll be seeing today is available, will be available on a PDF file and available for downloads. And then also to receive PDH credits in accordance with the professional licensing boards, respectively, of the individual states, you have to be participating in the entire program. Today's program will be 60 minutes in length. We'll have approximately a 45-minute technical presentation. And as I mentioned previously, we'll have a Q&A program immediately after the technical presentation. Next slide, please. To view the presentation in full screen at the top of your webinar is top of your screen, excuse me. You see webinar settings. Click on the down arrow, highlight view, and choose fit the viewer. Okay, everybody should be fine. Next slide, please. Now, finally, in my introduction, my great pleasure to introduce my friend and colleague, Brian O'Brien, works in our Madison, Wisconsin office. ARA, as you may recall, many of you know, we have about 50 offices nationally. Brian has got a doctoral and a master's degree from the University of Illinois. He's a principal engineer with ARA. He's got about 20 years experience. He's a professional engineer in 9 states in total. Brian, like many of our ARA specialists, subject matter experts, works both on the consulting side of the business. He's worked on, as you can see in slide number 5, over 500 general and commercial airports. But he has also been contributing and has contributed to the research and the development side of the topic he'll be speaking with you about today. And with that, I'd like to turn today's program over to Brian.
Well, thank you, Jerry. Good morning, everyone, or good afternoon, depending on where you're at. Here's an outline of my presentation so you know what to expect. I'm going to start out with some background on the pavement condition index procedure. That's really the backbone of airport pavement management and where everything started. From there, I'll shift gears into more of state of practice, talking about airport pavement management software, and then shift into state of practice on inspections, focusing primarily on comparing foot-on-ground methods to automated methods. And then I'll introduce some secondary concepts for pavement management, structural evaluations done according to the aircraft classification number, pavement classification number procedure, and I'll wrap things up talking about some ongoing or some upcoming FAA research efforts and how that might impact the future of airport pavement management. So historically, there wasn't a whole lot of management of pavements going on. Things were generally addressed in a worst first approach, meaning that those pavements in the worst condition received the highest priority to receive repairs. That started to change in the 1970s with the introduction of the PCI procedure and some proactive pavement management concepts, but that really didn't gain widespread adoption until the mid-1990s. But today we're firmly in that proactive category of pavement management, where we're looking to apply low-cost preventative treatments while the pavement's still in good condition. In order for this approach to be successful, timing is critical. And if we're doing things correctly, we're going to assign a higher priority to fix pavements that are still in good condition as opposed to those pavements that have deteriorated into poor condition. So the PCI procedure, again, was developed in the 1970s. The real impetus for that was the United States Air Force wanting to have a consistent way to evaluate and compare the condition of their runways at their Air Force bases throughout the U.S. and around the world. So they convened a panel of pavement experts who looked at a wide variety of different pavements, and they all agreed what condition they were in. They came up with this 100-point scale that you can see on the right, and looking at all those different pavements, all came to agreement that yes, this one's in good condition, fair condition, poor condition, and so on. From that, they then subdivided out all the individual pavement distresses that were contributing to why that pavement was in a certain condition. And they developed a set of nomographs. You can see an example of one here on the left. This is for longitudinal and transverse cracking on asphalt pavement, one of the more common distress types. And for a 5,000-foot sample unit, you would measure the amount of L&T cracking. From that, you would get a density. You would enter this nomograph, go up to your low severity, medium, or high, and then come across and get a DEDUCT value from that perfect PCI condition of 100. 70 is a very common trigger value or minimum service level used to initiate mill and inlay type of rehabilitation on asphalt pavement. You can see here at low severity, you would need 800 feet out of a 5,000 square foot sample unit. 800 feet of low severity L&Ts would drop you to a 70. Medium, you would only need 340 feet, and high, you would need 125 feet. Here's another example of another distress, rutting. You can see that this one is a more serious distress because it has higher DEDUCT values. L&T cracking is primarily an age and environmental related distress, whereas rutting is more of a load related distress. Typically, if we have rutting, it's going to indicate a failure of the base or the subgrade. And you can see here, correspondingly, we would need less quantity of rutting to drop us to a 70. For medium, 110 feet. For high, only 30 square feet of ruts would drop us 30 points. That's not very many ruts for a very big DEDUCT. Now, as practitioners really started to utilize the PCI procedure, they were coming across situations where they weren't sure, based on the guidance, the original guidance, what severity level they should call a certain distress, or in some cases even what the distress was. ECRO-Screen was one of the early pioneers in airport pavement management. They developed a guidebook that they published, and that provided a lot of additional criteria for their inspectors, allowing them to be more consistent and make better calls in the field. The PCI procedure was brought under an ASTM standard, D5340, in 1998, and when that happened, the ASTM officially incorporated a lot of those ECRO-Screen criteria, as well as some criteria developed by other consultants. Now that ASTM gets periodically updated. An important one to be aware of is the 2012 update, where they added a new distress type, ASR, or alkali silica reaction, to concrete pavements, and they separate out weathering and raveling as two separate distress types for asphalt. Previously, that was a single distress. The most current version of that, ASTM 20, was just released last month in October. These are all the different distress types in that ASTM that we're looking for when we do a PCI survey. There are 16 different distress types for asphalt, 16 for concrete, 17 for asphalt. Most of those are rated at 3 different severity levels, low, medium, and high, which means there's a matrix of almost 100 different distress type severity level combinations that we're looking for when we do a PCI survey. You can see in red, those are the distress types that changed under that 2012 update to the ASTM. So while some agencies were starting to adopt this proactive approach as early as the 1980s, as I mentioned previously, it didn't really get widespread adoption until the mid-90s, and the impetus for that was Public Law 103-305, which led to the FAA creating and instituting Grant Assurance number 11. And that grant assurance said that as of January 1st, 1995, any airport that accepts federal money to do pavement projects is agreeing that they will maintain that pavement for its useful life. Now, the reason for that grant assurance was the realization that this is just a more cost-effective approach. It's much more cost-effective to focus on preventative treatments where we can do crack sealing and patching when the pavement is still in good condition. It might cost $1 per unit of area, whereas if we let it deteriorate into a fair category, we might have to do something like a mill and inlay that's going to cost 4 to 5 times as much. And if it deteriorates into poor condition, something below a PCI of, say, 40, typically our only option is going to be complete reconstruction, which could cost 10 or even more times as much. So to summarize, the PCI procedure is composed of 3 things. The number between 0 and 100 is going to be determined by the distress type, the severity, and the quantity. Using those nomographs, that will roll up into a DEDUCT value. I will mention that for multiple distress types, there is a correction factor. In theory, with multiple distress types, you could get a negative PCI value, so that correction factor is applied. If you're really interested, you can look up the ASTM, but the computer programs they'll talk about under the software, they do all that for us automatically now, apply all those DEDUCT values and correction procedures to roll all those 3 things up into a PCI number that you can see in the scale on your right. And again, with this proactive approach, we really want to focus on preventive maintenance in these green categories. The fair category is typically going to be low-cost rehabilitation options like a mill and inlay on asphalt, or for concrete, it might be isolated patches and slab replacements. And again, we want to make sure we try to address things before they fall below a 40, where our only viable option then is typically going to be a complete reconstruct. Shifting gears now into state of practice with airport pavement management software. Here's the advisory circular that talks about the requirements of that, 5380-7B, and it lays out 3 main components that any pavement management software is going to need to have. That's going to be inventory, management, and reporting. Inventory is going to be things like, where is the pavement located? How is it subdivided into branches, sections, and sample units? What is the construction history? When was it built? Things like that. Management is going to be things that are typically customized by the user for a particular airport or agency. So it's going to look at the current and the historical PCI data and use that to develop family curves that will predict the future deterioration. Also programming the maintenance policies. So for instance, if there's this distress type, this is the type of maintenance action we're going to apply to it. Also things like assigning priorities, primary, secondary, tertiary pavements, things like that. And then reporting, getting out the current PCI value, the predicted future PCI value, when it's going to fall below that critical PCI where we need to program rehabilitation, things like budget analysis, unlimited, constrained budget, backlog elimination budgets, various economic analyses like that. 2 of the primary airport pavement management softwares are MicroPaver, and that's now just been shortened to Paver, and that's maintained by the U.S. Army Corps of Engineers. And then there's PaveAir, which was software developed by the FAA. They're both very similar. The FAA, big difference is that it runs completely over the web. You don't have to install any software on your machine to use PaveAir, and it's also free, which is great, obviously. Paver, the licensing there is not overly expensive, about $1,000 a year, but for some GA airports that don't have a lot of money to spend on things like that, it's nice to have that free option. They do both have a few pros and cons where one is better than another in certain categories for certain things. I won't get into all those details. I'll just say that they're both very viable, good options for airport pavement management. For structural evaluations, there's 3 primary softwares that I'll touch on. BACFA is one used to back calculate the strength of each pavement layer using non-destructive deflection data. COMFA is the software that we use to calculate the pavement condition number, the structural assessment that I'll go into some more details on, the ACN-PCN procedure. And FAARFIELD is the FAA's design software, and that can also be used to calculate remaining structural life. Lastly, ProFAA is some software to evaluate roughness. Now, both the Paver and the PAVAIR software have GIS capabilities. You can see an example of that in this photo here. That's an example of some GIS capabilities of PAVAIR. But most airports will export that pavement data into their own system. A lot of airports will be using AIRVIEW. Some might have more of an enterprise asset management, maybe something like IBM Maximo, a lot of different options out there. But typically, it's going to be easier for the airport people to use the software that they're used to rather than learning a new one. So we often will export that data to a separate GIS package. AIRVIEW is a website developed by ARA. We use that for a lot of our statewide as well as some of our commercial service airports. You can see a screenshot of that here. And we've also developed some unique structural display capabilities that I'll show you some screenshots in a little bit later. Now, viewing that data at a network level, and you can see some examples of that here. Each one of these polygons, these closed polygons, is a sample unit. And you can see a blow up of this particular sample unit right here. And you can see that Paver is capable of storing distresses for each individual slab. So each one of these boxes, each one of these squares is a slab, and you can see the distress is mapped out individually to each slab. But while Paver can store data at the slab level, it's only going to be able to display in a GIS format at the sample unit level. And you can see an example of that in the bottom right. Now, that's typically fine for network level studies where we're doing statistical sampling, typically maybe 33%, 30%, somewhere in there of the pavement. But if we're doing a project level evaluation where we're maybe getting ready to go to bid and need to have some more exact quantities on slab replacements or crack sealing, we might need to do a project level study where we're surveying 100% of the pavement. And some examples of what that might look like in a GIS output are shown here, where in the top left you can see we're displaying it more as a heat map of the pavement condition as opposed to individual sample units, more of a heat map type display. And then in the bottom right you can see all these red lines. Those are actually the cracks where they're located or the other distresses, and a way to show that data on a project level. So continuing on with some state of the practice for inspections, and again, we've got several viable alternatives here. We've got the traditional foot-on-ground approach. That's typically going to be done with a GPS tablet computer. You can see an example of that on the lower left. We've got image-based surveys with either a digital survey vehicle or an unmanned aerial vehicle, or an automated or semi-automated survey using something like a laser crack measuring system. When I say image-based, I am referring to what you would consider a typical image taken from a camera. The LCMS generates images, but they're actually a little bit different. They're generated from that laser data as opposed to being a traditional image, camera-based image. Now I'm going to attempt to, in the next 5 minutes or so, condense an hour-long ASCE webinar into just a few slides. So it's going to be very high level, but certainly encourage anyone that would like additional details to check out this ASCE webinar. It's got a lot of great information talking about the pros and cons of various survey methods. If I have to sum up that webinar in one slide, it would be this: everything's a trade-off. You can't say that one method is always going to be better than another method. They each have their pros and cons. So for a foot-on-ground approach, the biggest pro of that is that's the only method right now that's going to reliably be able to classify all of those ASTM distress types. One of the cons, however, though, is that you're not going to have 100% coverage of photos to be able to use later. We're certainly going to take a lot of photos with the foot-on-ground survey, but they're going to be maybe one photo per sample unit as opposed to 100% coverage. That's one of the big pros of the LCMS approach, is that we're probably going to start with a network-level survey for pavement management, but if we're doing that with an LCMS, we'd have the ability to go back later and do a project-level survey off all that data because we have 100% coverage of images. A big con, though, of LCMS is it's going to have trouble identifying some distresses that are very important to airfield pavements, and it's also not going to be very well suited to aprons. LCMS is really designed to drive in a straight line down a runway or taxiway. You can see kind of an example of how that works here, which means on an apron pavement where you've got aircraft or parked around gates or other obstacles, it's not going to be well suited to weaving in and out and around those obstacles. How the LCMS works, you can see here, it's got two lasers, one that's pointed straight down and another laser that's at an angle, and that allows us to generate a three-dimensional image of the pavement surface. It also has on the front of the vehicle a laser bar, and that's going to be able to use to measure the pavement profile or the roughness of the pavement. Also going to be used to determine vertical distresses, things like rutting. And you can see an example schematic of how that would work here. On a road, it's really easy to automatically identify the ruts because that laser bar is going to extend pretty much the full width of the lane, and those ruts are going to be located in wheel paths. So we know where to look for them. We can, with AI, be able to find those automatically because we know where they're at. It's a little bit harder on airfield pavements, and I'll show you some examples of why that's the case in just a minute. Here we have some examples of what those images look like. Again, these are not a camera image, they're images generated from that laser data. You can see the two-dimensional image from the laser pointed straight down. That's typically called an intensity image. You're going to be able to see paint markings, things like that. This is the exact same location on the pavement. That three-dimensional image, it won't show paint or stripes on the pavement, but it does give us a much higher resolution in terms of the ability to see cracks. You can see we're able to see much smaller cracks in this three-dimensional image than we were able to see in the 2D image. Current state of practice with LCMS, the top-end equipment can see millimeter and even sub-millimeter cracks, so you're able to see very small cracks. Now, when I refer to automated, this is a real benefit of the LCMS, is that we just run that through some computer programs, and it's going to be able to automatically trace all those cracks, and it'll put a different color on those cracks based on how wide they are. However, while it's really good at doing that automatically, it's not so good at differentiating between, is that crack an LNT crack, is it a joint reflection crack, is it a block crack, or is it a slippage crack? So this is again from that ASCE webinar, and this is really kind of the industry consensus right now on what AI is able to do reliably from a completely automated approach. These distresses in blue, it's pretty good at identifying without any human involvement. But you can see that's only a small subset of the distresses that we're looking for in a PCI survey. Now, if we get humans involved reviewing those images, we can do a lot better. All these other distresses in black now, we're able to get those pretty well in what I would call a semi-automated approach, where we have humans looking at the images and refining what those should be called. But there's still some distresses shown in red that we're really only able to get with boots on the ground. I had mentioned rutting being more difficult to identify on an airfield than on a road. Here's an example of why that might be the case. If we're driving an LCMS, we're going to be driving a parallel to the taxiway, some kind of straight lines this way. And you can see that the planes backing off this concrete ramp are creating some pretty big ruts as they back off that concrete onto the asphalt. And those ruts are going to be located perpendicular to the direction of travel of the LCMS, which is basically opposite of where you expect the ruts to be. And so those might get misclassified as depressions. There are ways to kind of address this issue, but I'll just say that it's a problem that's not completely solved yet. And I know a lot of airports that have used LCMS have had trouble with that, not finding ruts that were present. UAV, it's a hot topic right now. Everyone's looking at what they can use unmanned aerial vehicles, drones, what they can do with those. A lot of agencies are exploring the possibility of using those for PCI surveys. This particular agency was using a Phantom 4 drone, an off-the-shelf drone, very popular model, comes with a 20 megapixel camera. And this is an image that they took of one of their runways. They were flying at an altitude of 120 feet. And that looks like a really good image. You might look at that and say, why can't we do a PCI survey off that image? And to answer that question, I'll quote Matt Damon from The Martian and say, let's do the math. So at 120 feet altitude, a 20 megapixel camera is going to take a picture that covers a width of 78 feet. That means that we're going to have 4.8 pixels per inch. That means that the smallest crack we're able to identify is a 1/4 inch wide. You can see this red circle here. We have a blow up of that area right here, and that's the full resolution. These paint stripes are about 6 inches wide. You can see we've got a really wide crack here with some grass growing through it. Looks to be perhaps a very small crack here, but I can't tell for sure what's going on. We definitely have a crack here, but I can't tell whether that's sealed or whether, if it is sealed, whether the sealant's in good condition. And all those things are going to be critical to know, to be able to accurately identify the severity level of those distresses in a PCI survey. So certainly some limitations currently. There are ways around that. We could fly that at a much lower altitude. That would increase our resolution. We could use a drone that's capable of carrying a bigger, bulkier, heavier camera that has much higher megapixel resolution. But even doing those things, we're still going to be faced with some of those same issues that I showed on that previous slide of LCMS data. It's not going to be an automated approach. We're still going to have humans looking at those images, and we're still not, there's still going to be some distresses that we're only able to get with boots on the ground. So shifting into some secondary considerations for pavement management, PCI is really only focused on the condition of the surface. To get a more holistic overall picture of what's going on, we need to incorporate some structural assessments of the pavement. And the way we do that is with the ACN-PCN procedure. It's pretty simple in concept. Each aircraft has an aircraft classification number that you can look up, and you compare that ACN to the pavement condition number. If your ACN is smaller than your PCN, you're good to go. You can land there, no issues. If your ACN is larger than the PCN, that indicates that the pavement cannot support that aircraft. This is the advisory circular that covers how you do ACN-PCN analysis. First came out in 1983. The methodology was completely revamped and changed in 2011. They went to a cumulative damage factor approach. And the latest version of that, 5C, came out in 2014. I just want to mention that it is a different procedure from FAARFIELD, and you will occasionally get different results. There are some edge cases where you might design a pavement with FAARFIELD, and then you run those same design inputs through COMPA, and it would tell you that your pavement was insufficient for your traffic. So that doesn't happen often, but it is a known issue, and that's one of the reasons the FAA is currently working on a new procedure, an ACR-PCR procedure that will ultimately replace the ACN-PCN. Regardless of what process we're using, there's going to be three things we need to assess the structural condition of the pavement. Those are going to be the pavement layer thicknesses, the subgrade strength, and the traffic. For pavement layer thickness, the most common way to get that might be with a core. A better way might be with ground penetrating radar. See an example of that here. Shoot a radar signal into the pavement. Each layer is going to have a different dielectric constant, which is going to cause that radar signal to reflect back at a different angle. And from that, we can determine the thickness of each one of those layers. Some reasons why GPR might be preferable to cores. One is it's non-destructive. Two is, as you can see from this example on the left, the design thickness for this apron was supposed to be 8 inches in green, but the thickness varied anywhere from 4 inches all the way up to 14 inches. So if we had just done a few cores, it might be a little bit of a crapshoot on where we took those cores, what we thought the thickness of that apron was. With ground penetrating radar, we get a fuller picture, or better able to determine what's going on. And we can also see some subsurface issues like voids that you can see in this example on the right, underground utilities. We can see those and map those out with ground penetrating radar. The other thing we need to know is subgrade strength. A common way of getting that is with a falling weight deflectometer. You can see an example of that in this picture here. What that equipment does is it drops a weight on the pavement, doesn't damage it at all, it's non-destructive, but that has a series of sensors. There's one located underneath of the load plate, and then they're spaced out all the way out to 72 inches. As that weight drops onto the pavement, it causes it to deflect. The weaker the pavement is, the more it will deflect. We can run those deflection data through a back calculation program like I mentioned previously. There's a number of programs that can handle that. And what it'll do is determine the modulus of elasticity of each one of the pavement layers. And from that, we can then get a subgrade CBR or a K value, which are one of the inputs we need to calculate a PCN. Last thing we need for a PCN is traffic. And we need more than just operations or departures. We really need that traffic broken out into individual aircraft types. We need to know how many Airbus A321s there are, how many Boeing 737s there are, so on and so forth. That PCN number is going to be displayed as a code. It's not just a simple number. Rather, it shows up in this format where you've got a numerical value followed by a code representing whether it's flexible or rigid pavement. The next code is going to tell you what the subgrade strength is, and that's followed by a tire pressure code and then an evaluation method code. What that means is, correspondingly, there is not a single ACN number for an aircraft. Each aircraft has 8 ACN numbers, 4 for flexible, 4 for rigid, and then broken out by each subgrade strength category, high, medium, low, and very low. So when you are comparing your ACN to your PCN, you need to pay attention to those codes, make sure you're selecting the code, your ACN code that corresponds to the correct pavement type and subgrade strength from that PCN. So for an example here, the Boeing's 777 is one of the most damaging aircraft in the fleet right now. Flexible pavement, subgrade category low, has ACN of 87 at the maximum takeoff weight. Previously, a lot of the structural reporting was done by just gross weight. So you might have a runway, for example, that was rated for a dual tandem gear for 250,000 pounds. One of the reasons that we moved away from that to this ACN-PCN procedure is that weight really, the damage that an aircraft does, weight's not the most important thing. What really drives it to a large degree is going to be the gear configuration, the spacing between the tires, the tire pressure, things like that. So what might be counterintuitive, I'll give you an example of that. The Boeing, let's talk about the Airbus A380, one of the heaviest aircraft out there, maximum takeoff weight, a little over 1.2 million pounds. You can see the ACN of 80. Well, the Boeing 747 and Boeing 777 both weigh significantly less than that Airbus A380, but they both do more damage to the pavement, as represented by the higher ACN numbers here. Another example of that would be, let's look at that 747 again. At its empty weight, which would be a little under 400,000 pounds, the ACN is a 27. An Airbus 321 maximum takeoff weight is about 200,000 pounds and an empty weight of about 100,000 pounds. And you can see here that even though its empty weight is only a quarter, 100,000 pounds versus 400,000 pounds for a Boeing 747, they both do about the same amount of pavement damage, an ACN of a 27 versus a 26. So if you're not an engineer, maybe an airport administrator, you might be thinking, this is kind of complicated. Surely there's an easier way to figure out if my pavement can handle a certain aircraft type. And that's something we've heard from a lot of people. So one of the things that we developed to simplify the reporting of that was built in some drop-down windows into our AIRVIEW, where a user can go in, they can select an aircraft, and the software will automatically match that to the proper PCN code and generate a 3-color operational map showing where that aircraft can operate and where it can't. So green means the ACN is less than the PCN, you've got no issues. Yellow means the ACN exceeds the PCN, but it's within the FAA's allowable overload guidance. FAA typically says if a variety of certain conditions are met, that you can still operate. If your ACN for rigid pavement is no more than 5% greater than your PCN, for flexible pavement, they say 10%. Talk a little bit more about that later. But those fall within the FAA's allowable overload guidance, and we show those in yellow, which basically is just a caution. FAA typically leaves that up to the discretion of the airport manager. And red means that you exceed even those overload conditions. You definitely should not operate that aircraft there. So one of the airports we work with, these red areas, is typically where they'll do some overnight parking, where they don't have enough room at their gates. One question we got from them was, they normally wouldn't park a 747 here, but they were short on space, wanted to know if they could park it there. And you can see the answer is no. At the maximum takeoff weight, that would be a problem, could damage that pavement. But we can move that. Another easy thing, nice thing about this tool, we can vary that with this slider bar anywhere from the empty weight up to the maximum takeoff weight. And you can see that at the empty weight, that aircraft could park there, no problem, would not cause any issues or damage the pavement. So heading into the home stretch, talking a little bit more about some ongoing and upcoming FAA research projects and how that might impact pavement management in the future. I showed you that slide on the kind of industry consensus of what AI is capable of doing right now in terms of automatically identifying various distress types. I will just say that there's constant improvements being made in that field, so over time, that chart's going to change. AI is going to get better at identifying many of those ASTM distress types. I won't read the rest of these bullet points. I've got a slide for each of them, so let me just jump now to FAARFIELD 2.0. This new version of the FAA's design software should be released this year. It's going to have a new graphical interface. It'll follow the same design procedure and give you the same results as the current version 1.4 rather, but it will introduce the new ACR-PCR procedure that will ultimately in the future be replacing that ACN-PCN. Some future considerations that FAARFIELD will be moving towards will be integration of a top-down cracking failure model for rigid pavements, and also looking at improved modeling based on the results of an ongoing FAA research effort to figure out what they need to do to extend the design life of airfield pavements from the current 20 years all the way out to 40 years. Here's just an example of what that new FAARFIELD graphical interface looks like. It will a lot more user-friendly, more intuitive, easier to use. Talked about the FAA ongoing FAA research trying to figure out what they would need to change in their design procedures to go to a 40-year design life. And one of the realizations there is that pavements can fail from a number of different mechanisms. Right now, we're primarily just using PCI as the definition of failure. And that works out pretty well for a 20-year design life, because typically when your PCI is going to get into those 4 categories, you're also going to be experiencing issues with foreign object debris damage, probably going to have some load-related distresses, and your pavement's going to be starting to get rough, and you're going to probably be starting to have issues with friction. But that might not be the case when we go to a 40-year design life. We could get failure mechanisms from any of those individual items that may not line up with how they currently do with PCI on a 20-year design life. So the FAA is going to be moving to a serviceability level concept to manage pavements, and that serviceability level index is going to have these subvariables: PCI, foreign object debris, structural condition index, roughness, and friction. And what I take out of that in terms of what that means to airport pavement management in the future is that there's probably going to be a need for a lot more data collection. If we're going to be managing our pavements not just to a PCI, but rather to a serviceability level, and that serviceability level is composed of all these variables, we're obviously going to need to track those and over time as part of the pavement management program. Another FAA research effort that's getting ready to kick off is looking at roughness and new models for roughness. I talked about that Pro-FAA software, and what we can do is feed in a pavement profile to that, and Pro-FAA will calculate a number of roughness indexes. Straight edge is one that's commonly used with newly constructed pavement. There's construction criteria. It has to meet certain straight edge requirements. One of the most commonly used and well-known measures of roughness is the IRI, the International Roughness Index. What that does is it uses a quarter car system. You can see an example of that here. And it measures the cumulative amount of movement of the suspension of that quarter car system divided by the traveled distance. So that would be expressed in units like inches per mile. Brand new pavement, very smooth, might have an IRI of 60. The traveling public's generally going to rate pavements with an IRI less than 100 as acceptable. Start to get complaints above that, above say 150, you're going to have pretty unanimous agreement that the pavement is very rough, and traveling public's not going to be happy with that. The problem with that in terms of airports is it doesn't mean the same thing. As you might imagine, the suspension of a plane is not going to perform the same as the suspension of a car. One of the ways that the FAA looks at roughness is with the Boeing Bump Index. That's a better measure of roughness for airfields. But this is not focused on passenger comfort, kind of like IRI is measuring the movement, which translates to passenger discomfort. Boeing Bump Index was more devised to limit stresses on the airframe. And so it's really looking at single bump events, which doesn't really correlate to whether or not the pilot and the passengers would consider the entire length of the runway to be unacceptably rough. So the FAA is currently getting ready to kick off some research that will try to redefine that. They might come up with an entirely new index. They might refine the Boeing Bump Index to be able to handle multiple bump events. They're also getting ready to do some research looking at small unmanned aerial systems. They're going to be evaluating a series of sensors, both the traditional camera sensor, going to look at LiDAR, thermal, and hyperspectral sensors, and they'll be performing PCI surveys off that data collected with the UAS and doing direct comparisons to the PCI determined from foot on ground, as well as DSV and LCMS approaches, and the results of that will tell us whether this could ultimately replace those programs and be able to do just the UAV survey, or whether it might just be more of a supplement, something like good at detecting FOD. Last item, some research going on to characterize materials, things like warm mix asphalt. The FAA has their full-scale test track to look at things like that. And they'll build a pavement section, be able to traffic it rapidly to failure, look at new materials. Also looking at the overload study, I mentioned those 5% and 10% requirements. Those are really based on empirical data, not a lot of engineering data on that, so they're looking to confirm that those are the correct guidance for an overload scenario. Last item, this is not research that's going on at the FAA, but I find it really exciting. I wanted to bring it to your attention. I'll pose you the question, can the accelerator or can the accelerometer in a smartphone replace a Class 1 profiler? So ARA has been doing a lot of research on this, particularly in the land side, looking at crowdsourcing data collection that have people being able to collect IRI data in real time on their roads. We had an opportunity to evaluate that on airports under a research study with Missouri Department of Transportation. This was looking at their non-NIPIAS airports, specifically trying to see if we could come up with some lower cost alternatives. These airports are not eligible to get AIP funding from the FAA, so anything to lower the cost of an inspection would be a welcome addition to a non-NIPIAS airport. And working with our partners at the University of Missouri, Bill Butler and his team ran that profile data we collected with a smartphone through some artificial intelligence techniques, specifically genetic programming. And they were able to, based just on that IRI data, predict the foot-on-ground PCI value with 85% accuracy. So to answer that question, can a smartphone replace a Class 1 profilometer? The answer is not yet. The sampling rate isn't there yet to calculate a BBI, a Boeing Bump Index, but I can certainly see a future where airport managers have an app on their smartphone and they turn that on when they drive their runways and taxiways and gives them real-time feedback on the condition of their pavement. So rather than only doing a PCI survey once every 3 years, being able to have that real-time data and know immediately when your pavement condition is starting to deteriorate would let us make much better pavement management decisions in the future. Thank you very much for your attention. I'm going to turn things back over to Jerry.
Yes, Brian, that was fantastic. Wonderful delivery. Before we get to the Q&A program, as we always do, we'd like to share with you what's on the horizon. I would like to opine in particular on the December 16th program, Mask and COVID-19, a Practical Perspective. Now, you're probably all getting tired of hearing about mask, but a little bit of background that might entice you to invite others to participate is that a little known fact is ARA has and is currently doing federal government research for a number of agencies related to respiratory protection devices, the more technical term, obviously, for mask. And I just want to mention just a few of the outcomes that Brian will be covering, a different Brian, is you'll be able to understand the various types of RPDs that are available and the pros and cons of each. You'll acquire a practical understanding of the research that's been done and is ongoing related to respiratory protection devices. Understand this concept of what's behind source control and why it's important. And finally, you'll be able to make an informed decision. So this particular program might appear at first blush to not be of interest to anybody. You're probably in an overload mode. I think with that as learning outcomes, you might be enticed to invite your significant other, your children, and perhaps some of your pets to sign into that particular webinar. All webinars are recorded. We'll be mentioning that. You can see we have our program lined up. January through March is shown on this slide. In actuality, we've got topics and presenters lined up through September 2021. Next slide, please. Now for the question and answer period, and Brian Aho has been kind enough, again, excellent presentation, to share his web address with us, so his email address rather. So if we don't get to everybody's questions, we'll Brian will certainly respond to you on questions that he might receive after the program. But we do have a couple of questions. We'll go through those with you as best we can. And we've got ample time. So related to ACN, and Brian, I'll ad-lib some of these or interpret and paraphrase some of the detailed questions. Related to ACN values, who owns and calculates the data for the values per aircraft, or which source or organization is known to keep the best up-to-date database on this particular topic?
Great question. I struggle with getting up-to-date information on that myself. The aircraft manufacturers are responsible for publishing the ACN number. But sometimes those are hard to track down and find. Probably the best source that I've found for a comprehensive list of ACN numbers is a document put out by Transport Canada. And if you send me an email, I can shoot you a link to where that's located.
Okay. I'm going to kind of go through these in rapid fire. We've got about 10 minutes for things. Next question is it realistic to expect that a 40-year pavement design life is achievable?
Good question. I'll say it depends on how you define that. The answer would be yes, but the understanding there is that, and the FAA realizes this, you're not going to build a pavement and then not touch it for 40 years, particularly with an asphalt pavement. You're going to have a sacrificial wearing course where you're going to do maybe a 4-inch mill and inlay, or if you're a GA airport, a 2-inch mill and inlay periodically within that 40-year period, and that would still be meeting that 40-year design life criteria. They're really looking to limit structural issues over the 40 years.
Okay. Next question is, do you know or can you guesstimate when FAARFIELD version 2 will be released?
I'm hearing the answer to that is imminent. I would definitely expect it to be out before the end of this year.
Well, next question is, how common are asphalt surface treatments related to airfield pavements, and are they cost effective?
They're very common on general aviation airports. We see surface treatments done a lot. Less common on commercial service airports. They are very cost effective. From all the data we've seen, surface treatments are very cost-effective means of extending the life of those asphalt pavements. The main reason we don't see them as much on commercial service airports is the FAA has some weight limitations. Typically won't allow you to apply surface treatment to pavement that experiences aircraft over 60,000 pounds. They are getting ready to do some research in that area, so that may change in the future, but it's one of the limitations right now on some of those surface treatments.
Okay. Next question is, our agency uses a 10-point rating scale for roads. Are airports required to use the PCI procedure?
They are not required to, but they are encouraged to through kind of the funding mechanism. I would say that, so what the FAA does is they say that if you follow the very rigorous PCI procedure, that you only have to do a survey once every 3 years. They will allow you to do other methods, but if you do anything other than a PCI, they require you to do that annually.
Okay, next question. And I've got two questions here. We can accommodate questions because we've got about 3 to 4 minutes left, so don't hold back if you folks still have other questions that you haven't submitted. Next question is, how long, Brian, do you believe it'll take before technology renders foot-on-ground pavement evaluations obsolete?
Well, I would say it depends on the application. I would say for landside applications, we're already there or pretty close to being there. Because landside, we don't always have to follow that PCI procedure, and we can, through automated methods, pretty well replace that. For airports, it's going to take longer. I would say until we can move away from that ASTM or until the AI gets much better at pattern recognition to find those distresses, it's going to be a little while yet.
Okay, and the final question, and we have, those of you that are still with us, I've got 2 more slides I need to cover with you. So final question, Brian, that I have right now is, when will the new ACR-PCR procedure replace the ACN-PCN procedure?
The FAA allows some lead-in time. So when that software is released, and there's actually a beta version that's available on the FAA's website right now, if anyone is really interested to start checking out FAARFIELD 2.0, there's a beta version, and they can start calculating ACR-PCRs. But currently the guidance is that once that comes out, that the Part 139 airports would have until September 30 of 2023 is when they would need to be starting to report ACR-PCR instead of ACN-PCN.
Okay, and we do have another question that just came in. Thank you for your questions. That question is, has FAA ASTM approved the use of UAV for PCI surveys in lieu of fog? And what is really 2 questions here. What is the budgeting cost per square foot per yard asphalt concrete for GPR testing?
The FAA, so go at those one at a time. The FAA hasn't specifically said yes or no, but there are certainly agencies and airports that have done PCI surveys with UAVs. So it's not a matter of the FAA's, granting explicit acceptance or saying that you can't. They're kind of leaving that up to the airports right now and what the best meets their needs. The second question, cost per square foot on GPR, there's way too many variables that would go into that for me to answer that, but I can try to follow up with a little bit more detailed guidance, really, but it would need a little bit more information to give solid numbers on what that would be, but I can provide a range and can send that person some info.
Yeah, and whoever asked the GPR question, I might add, we did have, presented by our colleague Joe Ryder, a webinar dedicated on GPR in that recording. I'll tell you where to get that in a minute. So next slide, please. So for everybody joining today, for the full hour, you'll be receiving a PDA certificate and a copy of today's presentation in PDF form, and that's based on our attendance list that certifies that you've attended the entire program. Please allow us 2 weeks to receive the certificate, and you can contact us at ARAwebinars.com if you've got any questions. All these programs are recorded. You go to ARA Webinars, you'll be able to find the location of all of the recordings. Just as a reminder, we've been doing these on a monthly basis since February 2019. And the last slide, please. ARA is a company of about 1,500 people, as I mentioned previously. We have about 50 offices in round numbers around the country, always looking for the best and brightest people. And one of our mottos is science and engineering for fun and profit. So if you want to know more about ARA employment opportunities, you can use the information that's provided on slide 57, and we'd be happy to hear from you. So on behalf of Brian and myself and the ARA family, I want to wish you a blessed day, and thank you once again for joining us today. Hopefully you'll join us next month, December the 16th, and learn the truth and nothing but the truth about respiratory protection devices. Thank you.